So we're going to be talking about greatest common factor and least common multiple, right? Um, so let's start with the LCM because that's easier. So we're just talking kind of theory. What is the least common multiple? And it should make sense, right away just from the words least common multiple. And I've already got a different name for multiple. What's my name for multiples? It's two words, both begin with T. Hello, anybody out there?
Like the least common factor?
So greatest common factor. So, but what else do I call multiples? What's my second, third grade version of multiples? It's two words, both begin with T.
Timetable?
Times tables. That's it. So for me, I mean, I'm just old. It was times tables for me. Do you remember your 7 times tables, right? You can remember, just like you would study for a spelling test before dinner when you were a little kid, right? Same thing. All right, let's go through what's 7 times 3, right? That kind of thing. Or can you just list me the 12 times tables, that type of thing, however you would do it. So the least common multiple is easy if you can think of it as the first match of a times tables. So that's my version. First match. In times tables. And it's in quotes because it's a little bit suspect how I'm saying it maybe. So this thing and this thing is very important to us where we're going. We're going to fractions next. This is also called the least common denominator. Right? Least common denominator. So we're going to be finding, when we're doing fractions, we're going to be finding least common denominators, which is the same as the least common multiple. But what's the trick is we're using the denominator, right, the lower part of that fraction, as our times tables, right? So when I'm thinking least common multiple, I'm also thinking simultaneous least common denominator. And it's really important that we instill this, that fractions are easy, right? I mean, I have a half brother that's difficult, but doesn't mean that all fractions are difficult. We've got to really kind of hone in on this, how to make fractions simple so that there's not this fear of fractions that's I see so often, even in a calculus class, even in my best students, they have this fear of fractions for some reason. We've got to work together to get rid of it. You and I need you all to get rid of the fear that's happening. Is anybody here afraid of math?
No, definitely not. Never.
Exactly the kind of attitude and power I want to hear, even if you're lying. You've got to, and by the way, the students will still know if you're lying, no matter how good of an actor you are. So you actually want to build up this confidence anyway, Jordan. Thank you for Jordan. Thank God for Jordan. She's always positive and lying and speaking up. So the simplest way to find the LCD or the LCM is simply find the first match. That's all I'm talking about, right? So we might have a question. Find the LCM of 4 and 6, right? 4 and 6. So we're simply going to do the 4 times tables and the 6 times tables, right? So what do we got for 4? We got 4, 8, 12, 16, 20. I tend to go 5 and then see what happens. But 6, 12. Okay, I'm done. As soon as I see the first match, I'm finished. LCM, I have it. The least common match, the smallest number in both sets of times tables. And of course I could do it with 3 numbers, right? You can imagine if I did 2, 4, and 6. Find the LCM, right? Find the LCM of 2, 4, and 6. So then I'm just going 2's, okay, 2, 4, 6, 8, 10, 12, 4's, 4, 8, 12, 16, 20, 24, 6's, 6, 12, 18. Okay, I got a 12. As soon as I get my answer, right? As soon as I get a match of 12, I've got my least common multiple. There's an interesting problem in real life, the hot dog problem. What's the hot dog problem? Anybody eat pink? I call them pink missiles of death. My chair is squeaky. I gotta use some DW40 on it. What's the hot dog problem? Who eats hot dogs here? Anybody? Pink missiles of death, I call them. Edward, you eat hot dogs. Have you ever shopped for hot dogs? Daniela, yes? Shop. Who has shopped for hot dogs? And by the way, the hot dog I like right now is called an Honest Dog. Yasmiri's never eaten a hot dog. not shopped for one. Honest Dog, I'm telling you, try this hot dog. It's called an Honest Dog. You get it at Whole Foods, which I also call Whole Paycheck. It's very expensive, but these hot dogs are good. So, who's shopped for hot dogs? Please, somebody tell me you've shopped for hot dogs before.
I have, but I don't know how it's going to connect.
That's no problem. Not since I was little was Giovanni. So, hot dogs are usually sold in packs of what?
12?
I think you're right. I think like if you bought like Oscar Mayer hot dogs, it'd be a pack of 12. But what about the rolls? How about the hot dog buns? What are they sold in? 8. What the hell are they doing to us? Right? What is the conspiracy going on that I can't just buy some hot dogs and some rolls easy, right? So I have to. Now it works out for me because my girlfriend won't eat the bread, so she doesn't want the bread. She'll just put mustard and whatever relish and. So, but the idea here is, yeah, what do you mean, Yasmiri? What? What are you saying to me? Yasmiri, what are you saying to me? What's the what mean? No bread? Oh, okay, no bread, yeah. Well, there's some people that have dietary restrictions, like I'm diabetic, so I should not be eating bread or hot dogs. But, sometimes you're at a baseball game, what are you going to do, right? So there's an interesting problem in LCMs with hot dogs. It actually happens other times too, right? So the whole idea is how many packs of hot dogs, right? If hot dogs come in 8s, right? So hot dog, I know it's a horrible food, but hot dogs in a pack of 8, right? And rolls in a pack. Oh, no, we said 12, right? In a pack of 8, right? And so how many packs of each do I have to buy in order to have everything match up and not have extra hot dogs or extra rolls? Right? So if I think about that, I'm going to do an least common multiple of 12. So 12, 24, 36. Help me, 48. What's next? 60. Let's see what happens with the 8. 8, 16, 24. Okay, so how many packs of hot dogs did I have to buy? 2, because that's what multiple I got up to. And how many packs of rolls did I have to buy? 3, because that's where I got my match of 24 hot dogs and 24 rolls. So it's something that does happen in real life. Not that, it's not it's not like a life-saving problem to solve, like cancer, right? So another way to do both of these problems is that birthday cake or chandelier method, or what does the book call it again? I forget what it calls it. We'll see it again in the activities today, but I call it looks like just a chandelier to me, or wedding cake, a layer cake type of thing. But let's look at the greatest common factor now. How is this? Is everybody comfortable here?
Yes.
Thank you, Danielle. Let me take attendance real quick. So the next thing we want to talk about is the GCF, right? And we're talking about greatest common factor. It's one of the things I love about these two things is that the word here is greatest, right? And in our LCM, the word is least, right? But it's a little bit misleading, right? So we had what did I do? 4 and 6, right? So the LCM of 4, 6 turned out to be 12, right? Notice that the least common multiple is what compared to the other numbers?
It's larger than
large. So this is a little counterintuitive. The least common multiple is a bigger number. And guess what? The greatest common factor is going to be a smaller number, right? So there's this.
So like 4 and 6, it would be 2.
Exactly. What's the yeah. So let me. I didn't get there yet, but yes, you have it right. So, but it's a little counterintuitive, right? You're thinking of a least common multiple. It should sound like a small thing, but it's not. It's right. And it's bigger, and the greatest common factor is actually smaller. So the easiest way to do the GCF, right, is to prime factor everything. So 4, right, is what? 2 and 2. 6 is 2 and 3. And I'm just looking for the matches. I'm just looking for the connections. And you'll see the birthday cake method is much easier on this than prime factorization method. Okay. So the GCF of 4 and 6 is 2. And by the way, it would be the product of all of the matches. So I want to write out my version of how do you find the GCF, or the definition of the GCF and the definition of the LCM. And why are we doing all of this crap? Because we have to deal with fractions. I'm telling you, everything. You'll see everything is going to come down to your ability to get students to do this process, and it makes the fraction process so much easier. If you can just get students to do this game, then the fraction game is so easy. And for some of you, it might start to click on fractions, or the issues you've had with fractions, right? It might just start to click. as we do this stuff. And we want that to happen. Are you going to have, so far on your praxis test, you're going to have rounding. Okay, we took care of that. You're going to have fractions on your praxis test. Hopefully we're going to get this too, right? So, we're just kind of chipping away, starting in what you're actually going to see on the praxis exam compared to what you need on the exam to be able to do the, right? So there's a process, but certainly you're going to have to round. I think that's the most important thing we did in chapter 1, rounding. All right, I want to give my version of a definition of the GCF and of the LCM, and it's going to be a little wordy, so I apologize ahead of time. A GCF is the product of the matches of the factors. So this is, again, this is a super nerd talking. Product of the matches of factors. So we had 4, which was 2 times 2. We had a 6, which was 2 times 3. The only thing that matched was a 2. So that's one match. It's a one match of 2. So the product of the first match is still a 2. You're not doing a 2 times 2, right? So I just want to take all of the matches and make a product out of them, right? So the GCF, again, 4 and 6 was just 2. Product of the matches of the factors. So if there's a match of 2, I need the product. Of course, there's always a match of 1, right? Does that make sense? There's always a match of 1, so I could. All right. So, but let's do 4 and 8. So if I have 4 and 8, so 4 is what? 2 times 2. 8 is 2 times 2 times 2. Right? Does everybody agree with that? Remember, I'm doing that prime factorization thing, and it's going to be easier when I do the birthday cake, wedding cake, whatever. So notice I have a match of 2 and a match of 2. So I have 2 matches. So the first match of 2 times the second match of 2. 2 times 2, the GCF is 4. So the GCF of 4 and 8 is 2 times 2 is 4. So the wording is not ideal, but hopefully I'm talking to other nerds here, and we can handle this kind of wording. Product of the matches, right? So if I have a match of 2, I need a 2 in my product. If I have a match of 3, I need a 3 in my product. If I have another match of 2, I need another 2 in my product, right? Is that making sense? Okay, LCM. It's the product of the matches and the non-matches. Product of the matches and non-matches. I always find it funny. You should never play with matches, right? I can't do GCF problems, man. I can't. I'm not supposed to play with matches. So product of the matches and the slide. Thank you, Daniela. Slide method. Yeah, whatever. Slide method. Thank you. Product of matches and non-matches. So let's look at the first one we did. We did a 4 and 6, right? So 4 was 2 times 2. 6 was 2 times 3. Okay, I have a match of 2. I have and I actually will write it like this. I have a non-match of 2 and a non-match of 3. So my LCM of 4 and 6 is 2 times 2 times 3, which is 12. So product of the matches and the non-matches. And believe it or not, I've taught college students this. When we're trying to so sometimes we'll have a fraction of like x over x plus 2 times x minus 2 plus 3 over x plus 2, and I have to get a GCF of this. So I go all the way back to this second, third grade piece and use this language. Product of the factors, the matching factors or the matching and non-matching factors. You remember this kind of hell in Algebra 2? Remember this horrible stuff? Where you had to all of a sudden do fractions with algebra involved? Anybody remember that hell? I'm not trying to trick you here. I want to hear the truth here. Does anybody remember doing all of this fraction stuff with algebra? Yeah, oh, Madeline says, yeah, I didn't like it. No one liked it. No one liked it. Giovanni says yes. The teachers don't even like it. I do, but no, I'm weird. Yes, Mary says yes. I remember that hell. Okay, we're ready for the layer cake method, birthday cake method, slide method. It still looks like an upside down. It looks like a chandelier to me. Right? You know what I'm saying? Yeah, you walk into that fancy restaurant, in the middle of the room is this giant thing hanging down with the lights, right? And all this crap hanging off of it. Chandelier method, layer cake. It's an upside down layer cake, right? The layer cake would work better the other way. So let's look at a fairly simple one. Let's say let's say 4 and 8 again, right? So we want to look at the GCF and LCM. We're going to do them at the same time, which is what's nice about this this method, right? With the cake method. So I want to look at the GCF of, what did I say? 4 and 8. Yeah, 4 and 8, question mark, and the LCM of 4 and 8. And I'm going to get them both at once. Okay? I'm going to get them both at once. So I'm going to get the matches, product of all the matching factors, and product of all the matching factors and non-matching factors. I'm going to get them all at one time. Okay? With this birthday cake method. So I like the birthday cake with the 2 entries or 3 entries or etc. Right? It's usually not more than 3. So I'm doing inside that first layer of the cake, I'm doing my 2 numbers that I'm trying to find the GCF and the LCM. And I don't care if I overachieve or underachieve. I actually prefer the underachievement. I'm going to see that both are even. So I'm going to divide. And yes, I can see both have a 4. Right, a factor of 4 in. So I'm trying to put matching factors on this outside piece. So matching factors on the outside piece, right? So 2 times what is 4 and 2 times what is 8. So I'm going to get a 2 and 4, right? So you see I'm kind of like doing long division there. 4, right? 4 divided by 2 is 2, right? 8 divided by 2 is 4. Or times, if you prefer to think of the multiplying, either way. And then rinse and repeat, right? So I see a 2 again. And my colors are meaningless here. So 2 times 1 is 2, and 2 times 2 is 4. We don't care about the 1s. Whenever they happen, we don't care, right? 1s are inconsequential to us. So I have matches of 2 2 matches of 2. And 1 non-match of 2. 1 leftover 2, right? So remember, the GCF, right? The GCF is the product of all the matches. So 2 and 2. And the LCM is the product of the matches and the non-matches. So 2 and 2 and 2. And there we are. So the GCF of 4 and 8 is 2 times 2. And the LCM of 4 and 8 is 2 times 2 times 2, which is 8. That's simple. So what gets built out on the left-hand side of this chandelier, or the slide method, are the matches. And what's left over at the end are the non-matches. Right? I didn't even have to write it at the end. I'm done. I'm done here, right? So 2 and 1 are my non-matches, even though 1 always matches. But we don't care about the 1s. The 1s don't change anything, right? The 1s don't change anything. All right, let's do a more difficult one. Ready? Let's do 40 and 18, or 18 and 40. So we want to find the GCF of 18 and 40 and the LCM of 18 and 40, right? Find the GCF and the LCM of 18 and 40. So we start with our first layer of the cake, and we throw in our 18 and our 40. Anybody see a number that goes in to both? Hello? Is there anybody there? If you were all asleep in my class right now, I'd be throwing pieces of chalk or erasers or probably.
Well, I know 2 goes into both.
Thank you. And do we care if we get the biggest number? No. Anything. Don't worry about being perfect. We're human. We're not perfect. So I get a 9 and a 20. And guess what? I'm done. Nothing else. So 9 is a 3 times a 3 or a 1 times a 9. 20 is 2, 4, 5, and 10. We're finished, right? So our GCF of 18 and 40 is the product of the matches. There's only a match of 2. Done. And the LCM of 18 and 40 is the product of the matches, which is 2. 2 is a match. It goes into both. And then a 9, and then a 20. Right? And so I need a little help there. 360? Is that right? Yeah. Done.
360,
Yep,
yeah.
that's it. It's that easy. Product of the matches, product of the matches and the non-matches. That's it. It's very simple. And the birthday cake method is really what makes it the most simple, right?
The birthday cake or chandelier thing is way easier than the other thing you were showing us.
Yes, absolutely. And I don't remember. I think I actually learned it in grad school. I took a how to teach math class and when I was a graduate student. And I had this teacher who, I think she was like 70 some years old, but she was so good. She knew all of these processes. And this particular process was from an American math teaching textbook from like 1920.
Okay, that's actually what they have at like most schools. The textbooks are so old.
Yes. Yeah. I mean, because we haven't changed much. I mean, that's an issue, I think. But if you think about what was happening in the 20s, what was happening in America in the 20s?
Prohibition.
Yeah, but drunk people don't care about math.
I don't really know anything anything else that happened. Oh, the stock market crashed.
Okay, the Great Depression. There was a Spanish flu. There was the flu that was basically COVID, and something else was about to happen. Actually, something did just happen. War. Modern war, right? So, I mean, there were wars before that, but now all of a sudden we had started making bombs. And so, and this is just my opinion, okay? So, but I believe in America, we had said we need to have a strong military, so why don't we make everybody do math so we could find the people that will be able to make us bombs. If we make everybody do it, we'll find out who's really good at that thought process. And this is an issue I have with learning math, right? There are countries where if you demonstrate that you have no interest in doing math, you don't study math, right? So, but what we were trying to do, I believe, is mass produce engineers. If we could make everybody go through this heavy math prep, we could weed out who's really good and then grab them. And of course, all the rest of us suffer. But anyway, I wish I didn't record myself saying that. But let's look at a problem from the homework. Okay.
And this is 8.5?
8.5, yeah. So I'm just going to pick some problems from 8.5. The theory, we're done. We're done with the theory. Okay. So we're done with the theory. There's an interesting reason, so I talked about the hot dog problem, right? But there's a beautiful problem in music that I used to be a musician anyway. But you'd always be practicing playing different rhythms. So playing fives. Right, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. But most music is in 4, right? So 1, 2, 3, 4. 1, 2, 3, 4. So if the drummer's playing 4s and the guitar player's playing 5s, when do they meet up again? And this is right. This is exactly this LCM problem. Right? If one person's playing 4s and one person's playing 5s, when does everybody come back together on 1? Right? Anybody want to try it with me? Anybody else a musician here?
Yeah.
Chris, you ready? You want 4s or 5s?
I'll take 4s.
Okay, so you're going 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, and I'm going 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And we're gonna see when we clap again. So we'll count off in 4 and we'll go. Ready? 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 4, 3, 4, 5. There we go. So that's an interesting thing when you're like, I used to play in a jazz group, and we'd all be trying to play in different times, and then you're seeing, okay, when do you all come back together for that big moment of the song? All right, let's try the first one here. Less interesting, but LCM of 27 and 63. It says do prime factorization, but let's do both. Okay. So prime factorization And then we're also going to do birthday cake. So 27 and 63. LCM of 27 and 63. So 27 is what? 3 times 9. 3 times 3. 63. Right, you're doing this with me, right? 9 times 7.
7.
Yep, 3 times 3. So watch how I do it with the tree, with the prime factorization, right? So 27 and 63. 27 is 3 times 3 times 3 times 9. And 63 is 3 times 3 times 9 times 7. I'm trying to hook up my matches and my non-matches. I'm trying to hook up the matches and the non-matches. And so now the product of everything across is my LCM. So 3 times 3 times 3 times 9 times 7. Is that making sense to anybody, to everybody? $17.01. Remember, my LCM is matches and non-matches. Right? The product of the factors that match, which I've lined up in red, and the factors that don't match with anything I've lined up with green. Right? Birthday cake, much easier. 3 goes in 9 and 21. It goes in 3 and 7. Oh, wait, where did I get the 9 from? I'm sorry, I made a mistake. There's no 9. Shh. Didn't anybody catch me? Remember, at the end, I'm just doing the primes at the end, right? So no 9, sorry. Silly Robert. 189 is the right answer. But anyway, matches, non-matches, 3 times 3 times 3 times 7, again, 189. That slide method, that chandelier method, birthday cake is so much quicker, so much easier. But we want the understanding of both. We want the understanding of the prime factorization, which came from our previous section, very important, prime factorization. And then the slide method is just quicker. We like quick, us humans, us Americans especially. Let's look at another one here. So it's not going to change much, but I would always just do birthday cake method unless they really wanted me to do this prime factorization. Oh God, that one looks horrible. Let's do this one. So at least so you can see me do one like this, because they're horrible. We're almost done today. So this is from the homework. This is homework 8.5, number 6. And it gives me 2 numbers. 2 to the 32nd power times 5 to the 15th power times 7 to the 22nd power, and 2 to the 34th power, 5 to the 23rd power, 7 to the 14th power. So what I want to do, and remember, what do we do when we multiply like bases? When we multiply like bases, what do we do to the exponents? So if I said like 2 to the 3rd times 2 to the 4th, that's 2 to the what power? Danielle, I'll get to 11 too. What am I on, 6? Yeah, I can do 11 also. So this is what, 2 to the what power? Well, this is 2 times 2 times 2, right? 2 to the 3rd is 2 times 2 times 2. And 2 to the 4th is 2 times 2 times 2 times 2. So how many 2's are there? 7. So you're adding exponents, right? When you're multiplying like bases, you add exponents, okay? So I would like to split this into 2 to the 32nd, and then 2 to the 32nd, and then 2 squared. Notice here that my 2 exponents add up to my 34, right? And then I've got a 5 to the 15th, 5 to the 15th, and I've got another 5 to the 15th, but how much more do I need to get to 5 to the 23rd? I need a 5 to the 8th. So notice that my 15 and my 8 add up to my 23. And now I have a 7 to the 14th, and I need a 7 to the 14th here, but I need how many more to get to 22? I need the 8. 7 to the 8th. So what are my matches? And I think we're asking for a GCF here. Yeah, GCF, right? So what are my matches? I match a 2 to the 32nd. I match a 5 to the 15th. And I match a 7 to the 14th. And the product of those is my GCF. So the GCF is 2 to the 32nd times 5 to the 15th times 7 to the 14th. So I got to split things up to be able to see where things match and where the leftovers are. GCF is the product of the matches. LCM is the product of the matches and the leftover pieces. How are we doing?
That's good. I was confused with it, but now I get it.
Yeah, and that's normal. There's nothing wrong with being confused about something. So I want to go to you, Danielle. You were asking me about 11.
Yes.
Yeah. Oh, good. So we're moving into this fraction piece. We want to basically we're going to find the GCF here. So we're trying to find the GCF of 240 and 460. So the question is written differently, right? But this is my interpretation. Find the GCF of 240 and 360. Am I right? Are those my numbers? I forget already. Because I'm not too... Oh, 460. 240 and 460. Sorry. And so I'm going to go chandelier because that's what I prefer. And I see a 10. I see a 10 right away. So there's a 24 and a 46. Okay, now I see a 2. I'm not thinking too much. I'm just saying, what do I see quickly? So I got a 12 and a 23. And guess what? 23 is prime. I'm done. So my GCF is 2 times 10. Remember, the product of the matches. The factors that match up that are in both. So I get a GCF of 20. Now, what's interesting is I can see a connection here between purple and a connection here between green. So watch this. I had 240 over 460. And that's 20 times 12. There's my purple. Over 20 times 23. So the 20 times the 12, the purple is the product, is 240. And the other one is 460. The product of 20 and 23 is 460, but these cancel, right? You can see my 20s will cancel. And so there's this is how we reduce fractions. Find GCFs. Kind of cool. Fractions are easy. What do you think about fractions? What's general opinion about fractions? Everyone, anyway, just yell it out. Chat it out. Yell it out. General. You got you got to learn to lie to me. If you can't lie to me, if you can't lie to your professors, how the hell are you going to lie to your teacher, your students? You love fractions. Fractions are easy. This is, I'm serious about this. Imagine you're driving your car and you go, oh my God, I'm going to get in an accident. Oh my God, the car's going so fast. If you're driving like that the whole time, you're in trouble. And maybe I'm in trouble too. That's worse. So when you're driving, you have to have confidence, right? When you're driving, you have to have confidence. When you're doing this math stuff, you need to be confident. If you're sitting there going, I hate this, or I'm no good at this, or I'm dumb, or this is difficult, right? It's just not the right mindset for anything in life. Yeah, so Danielle, the rest of those are all the same, I think, and I think that's the whole homework.
Okay, yeah, I got it now.
Yeah,
Thank
nice,
you.
nice. So let me do this one. Let's make this one our last problem today. So I'm going to do 7 over 24 minus 1 over 28. Okay? 7 over 24 minus 1 over 28. So this is, we're kind of, remember, the book has already taught fractions. Okay? But, right? If you think about chapter 1, chapter 2, chapter 3, we're in chapter 8, right? Chapter 2 is fractions, but we're doing the GCF LCM thing because it's what we need when we teach fractions. So I don't know, whoever wrote the book, that's what they prefer to do. But we want to do 7 over 24 minus 1 over 28. And the key here is that we need an LCM. We need at least an LCD. So we're going to do LCM, birthday cake method, right, with these two. So get someone yell out what you want to go with first. What number do you want to go with first? What goes into both numbers?
2.
Good. I like 2.
Right.
I like 2. I don't have to be perfect. I don't have to be quick. I just have to be right. So 2 again, right? So 6 and 7, and guess what? I'm done. Right? I'm done. 6 and 7 is prime, right? So I have a GCF of 2 times 2, and I have an LCM of 2 times 2 times 6 times 7, right? Product of the factors and the non-factors. Yes, see with me? So that downstairs, so 2 times 2 times 6 times 7 is my LCM, or my LCD. Okay. So, by the way, notice the green is what number? What's my green here? What's 2 times 2 times 6?
24.
Nice. So what am I missing is left over. So 7. So I'm multiplying this guy by 7 over 7. What about in purple? What's 2 times 2 times 7? 2 times 2 times 7.
28.
28. So what am I missing is a 6. I'm missing the 6 from the for the 28. So now look what I have. I have 49 over 168 minus 6 over 168, and now I can combine. Once I get the same denominator, all I have to do is think about the numerators. So what do I have? 43 over 168. And then I have to check if they reduce, okay? But they don't. In this case, they don't reduce. So you can see where this LCM is coming into place and where the secret pieces are missing from the fractions. Now, I am not too worried about you getting 8.5 completely right until I'm done with chapter 2. Does that make sense? So, like, there's a couple of fraction problems here in 8.5, but I haven't taught you fractions yet. So I don't, and this is why I like this homework due at the end of the semester, because there's weird overlap the way we've organized things. So there are some fraction problems in 8.5, but we didn't teach you fractions yet. I didn't say anything about what I did here, right? I didn't say anything about what I did here, So you're going to wait for me. And we're done today. I don't want to do anything else. I'm going to stick around. Victoria, you're going to talk to me